Ada nggak?
Cek, cek, cek 651.
Sama skripnya sedikit Mas Danang tuh.
Wis.
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 Tuh, skrip tak kena Mas Danang pimpinan nih.
Ya iki.
Wis.
Iki wis. Sono. receive my like title and abstract? I think.
Yes. I have received that. I'm sorry that I didn't give the feedback. I'm
Yeah,
really
no
sorry.
problem. Yeah, just to make sure. Yeah.
Good morning, distinguished keynote speakers, presenters, and participants. Welcome to the second day of the World Contest organized by Faculty of Engineering Universitas Negeri Malang, and part of the venue is today we are hosting the International Summit on Sustainable Energy, Functional Materials, and Industry, Isefmi 2025, particularly in breakout room 1. In this section, we also have a registration session. Please kindly complete your attendance through the link provided. While waiting, we also kindly remind all participants to set their Zoom name in the format of name and institution to facilitate the identification. So please wait for around 5 minutes for this event to start. Thank you. please allow me to introduce him. Professor Ming Chang Lu received his PhD in mechanical engineering from the University of California, Berkeley in 2010. He served on the Faculty of National Chao Tsung University from 2010 to 2019 before joining the Department of Mechanical Engineering at National Taiwan University in August 2019, where he currently a professor. Prof. Lu was elected Fellow of the American Society of Mechanical Engineering, ASME, in 2025, Fellow of the ASEAN Union of Thermal Science and Engineering, AUTSI, in 2023, and Fellow of the International Association of Advanced Materials, IAAM, in 2022. He also served as chair of the Taiwan Heat and Mass Transfer Society from 2020 to 2022. He received the Distinguished Young Scholar Award from the Society of Theoretical and Applied Mechanics, ROC, and the Tayo Wu Memorial Award from Taiwan Ministry of Science and Technology, both in 2015. Prof. Lu research focused on the micro and nanoscale heat transfer and phase change heat transfers. And in this presentation, he will show how small structures enhance phase change heat transfer, focusing on condensation and boiling heat transfer. So, how are you, Prof. Lu?
Good, yeah.
Yeah.
Can you see my slide?
Yes. It's very clear. Okay.
Okay, thank you.
Now you can start your lecture, and time and place yours, please.
Thank you. Thank you, Chairman, for the introduction. And I would also like to thank the organizing committee for inviting me to the conference. The title of my talk today is Small Structures for Enhanced Phase Change Heat Transfer. My name is Ming Zhang Lu. I'm from Department of Mechanical Engineering, National Taiwan University. Before I start, NTU was founded in 1928 by Japanese government during the Japanese occupation, and then renamed as a National Taiwan University in 1945 after World War II. And in year 2028, we are going to celebrate 100 years anniversary. NTU ranked as 16th in this QS 2026 World University ranking. National Taiwan University has many campuses. In Taipei, there are 3 campuses. The main campus located in the Gongguan area, and also there are Shiyuan and downtown campus in Taipei. Besides Taipei area, there are also Zhubei campus and Yunlin campus. And there are also important fields such as this highland experimental farm field and experimental forest. So total area of NTU around 1% Taiwan total area. Okay, and in today's talk, I will cover 2 topics. The first topic is 3-dimensional hybrid micro-nanostructures for enhancing condensation. And my second topic today is enhance the critical heat flux and heat transfer coefficient of pore boiling on a hybrid copper pillar array surface. So let me start with my first topic today, using 3-dimensional hybrid micro-nanostructures for enhancing condensation heat transfer. Condensation is a commonly seen phenomenon in our daily life. such as condensation on a water bottle and also dew on a leaf. It is also widely applied in many industrial systems, such as in electronics cooling or in power plants. Condensation can be classified into two modes. On the left-hand side is finwise condensation. The finwise condensation happens on a hydrophilic surface. During finwise condensation, a continuous liquid film forms on the surface. Because this water liquid has a large thermal resistance, this water film formed on the surface will impede the heat transfer between the solid surface and water vapor. On the other hand, right-hand side shows the dropwise condensation on a hydrophobic surface. During dropwise condensation, discrete liquid droplets form on the surface, and these droplets can be efficiently removed by gravity. After droplet removal, nucleation happens again on the surface, and these droplets are again removed by gravity. The process repeats itself. This efficient removal of liquid droplet enhances heat transfer coefficient. Compared to the finwise condensation, the dropwise condensation can give 5 to 7 times a higher heat transfer coefficient than finwise condensation. This slide shows the definition of a superhydrophobic surface. First, the liquid droplet has a large contact angle over than 150 degrees on a superhydrophobic surface. In addition, it has a small contact angle hysteresis, which is defined as the difference between the advancing and receding contact angle. As a result, liquid droplet can easily roll off the surface. Therefore, superhydrophobic surfaces can enhance dropwise condensation. We have been applying superhydrophobic surface for enhancing condensation heat transfer. This image shows these SEM images of a superhydrophobic silicon nanowire array. The nanowire has a height around 10 micrometer, and each nanowire has a diameter around 200 nanometer. The contact angle on this surface is around 145 degrees. The bottom figure shows the heat transfer coefficient versus subcooling temperature, which is the temperature difference between the saturation temperature and surface temperature. In the figure, there are results from the superhydrophobic surface, which are green open square here, and green triangles are results from the plane hydrophobic surface, and the red circles are results from the plane hydrophilic surface. The dark solid line is the theoretical prediction for finwise condensation. The prediction agree well with the result from the plane hydrophilic surface, which also validate our experimental result. So compared with this plane hydrophobic surface, the heat transfer coefficient can be enhanced by 87% on the superhydrophobic surface at low subcooling. But as we can see, this heat transfer coefficient decays significantly with subcooling, especially at high subcooling region. This is because the flooding happens on the surface. Once flooding happens on the surface, a liquid film forms on the surface, which impedes the heat transfer between the vapor and solid. So to address this flooding issue, recently we proposed this three-dimensional hybrid surface consists of superhydrophobic silicon nanowire array along with the hydrophilic silicon microchannels. This image shows the cross-sectional view of this 3D surface. The nanowire height is around 15 micrometer, and the height of the channel is around 50 micrometer. The contact angle on the hydrophobic area is around 150 degree, and the contact angle on the hydrophilic area is around 30 degree. Here shows the top view of this silicon nanowire array, and the height of nanowire is 15 micrometer, and the diameter of the nanowire is around 200 nanometer. The ratio between the hydrophobic and hydrophilic region is maintained as 1.5 according to the literature results. Here shows the condensation experimental system. The experimental system consists of 3 parts. First, the boiler, and second, the condenser, and finally, the impingement cooling system. In the boiler, we boil liquid water into the water vapor, and the vapor then flows through the pipe to the condenser. In the condenser, impingement cooling is applied at the backside of the sample surface. Therefore, this water vapor is condensed into liquid water on this condensation surface. This condensate then flows back to the boiler to complete the cycle. This condenser is a closed chamber with a pressure of 47 kilopascal with the corresponding temperature of 80 degrees. Here shows the picture of our taxation. The sample size is 2 by 4 centimeters square. This sample is surrounded by Teflon to prevent the heat loss. The bottom image shows the cross-sectional schematic of our taxation. This sample is bonded to a copper block using thermal interface material. Impingement cooling is applied at the backside of the copper block to carry away the heat from the condensation. 3 holes are drilled in the copper block to accompany 3 thermocouples. And using the temperature gradient from the 3 thermocouples, we can get a conduction heat through the copper block using the Fourier's law as shown in this equation. Then assume this condensation heat on the surface is equal to the Newton's cooling law, Q equal to HA times vapor temperature minus surface temperature. H is the heat transfer coefficient, A is the surface area. Then by equating these 2 equations, we can get the heat transfer coefficient of condensation. Here shows the condensation images taken on these 3-dimensional hybrid surfaces. We have studied 3 different channel widths. First, S1300 surface has a channel width of 1300 micrometer. This surface X600 has channel width of 600, and X300 surface has channel width of 300. And images shows the condensation happens at low, medium, and high subcooling temperatures. First, at low subcooling on this X1300 surface, you can see this condensate efficiently removed by gravity on this surface, and finwise condensation happens in the channels, and also dropwise condensation happens on the hydrophobic area. Similar phenomena can be observed on this X600 and also X300 surfaces. So in conclusion, we can say that the 3D hybrid surfaces can efficiently shed the liquid away from the surfaces. Here shows the heat transfer coefficient versus subcooling for the 3D hybrid surfaces, including the X1300, X600, and X300 surface, compared to the superhydrophobic silicon nanowire array surface, which is the yellow triangle symbols here, and also the plain hydrophilic surface. And this solid line is again the theoretical prediction for finwise condensation. The prediction agree well with the experimental result on the hydrophilic plane surface. So we can see that this condensation heat transfer on the superhydrophobic surface, although it's very high at low subcooling temperatures, but it decays significantly with subcooling. But these 3D hybrid surfaces can enhance condensation heat transfer at medium and high subcooling temperatures. Compared to this superhydrophobic surface, heat transfer coefficient was enhanced by 130% at medium subcooling and 85% at high subcooling. But we still see the gradually decay of heat transfer coefficient on these 3D hybrid surfaces. This is because although we consider these strawberries are superhydrophobic on the silicon nanowire array, they are actually partial window strawberries, which means that they are liquid stains underneath the liquid cap for this liquid droplet. These right-hand side figures are these environmental SEM images taken during the condensation process. So this liquid stain will impede the droplet removal during the condensation process. As the subcooling temperature increases, the number of liquid stain will increase. Eventually, this KC droplet will completely transfer to window droplet stuck on the surface, difficult to be removable at high subcooling temperature. This causing the decay of heat transfer coefficient on the superhydrophobic surface. So to address this issue and to maintain a constant heat transfer coefficient at the medium and high subcooling temperature, we propose this modified 3D hybrid surfaces with a shorter nanowire array. The concept of the design of this modified surface is similar to our previous 3D hybrid surface, but the major difference is the nanowire array now is much shorter than the previous case. The nanowire array height is only 1.5 micrometer compared to the 15 micrometer in our original design. Again, the surface consists of this superhydrophobic area with the nanowire array and the hydrophilic region in the microchannels. The contact angle on this superhydrophobic area is around 140 degrees. We believe this shorter nanowire array can minimize the chance for KC to window droplet transition and also reduces droplet friction during the condensation process. Here shows condensation dynamics taken on these 3D hybrid surfaces. The darker area are the hydrophobic regions, and these shiny area are the hydrophilic regions. First, we can see this condensation image taken on this 1300 surface. This number is again representing the channel width. First, a low subcooling of 3 degrees, and then medium subcooling, and finally the high subcooling. So we can see dropwise condensation happens on the hydrophobic areas, and finwise condensation happens in the hydrophilic area. The right-hand side shows the condensation videos taken on this N600 surface. Again, you can see this sustained finwise condensation and dropwise condensation happen on this surface as well. Followed by this surface is this N300 surface. A little bit difference is that we can see a large droplet across multiple channels on this N300 surface. We call these droplets the bridge droplets. These bridge droplets, if they stuck on the surface, they will impede the heat transfer. But in condensation, we see that in medium subcooling temperature, this bridge droplet can be sucked into the channels and then disappear from the condensation. This is because the high liquid velocity in the channel region will create a local low pressure area in the channel region. Therefore, this liquid cap is then sucked into the channels, and these bridge droplets are safe eliminated during the condensation process on this N300 surface, as we can see from the video. Then on this N100 surface, initially there are also bridge droplets happens on the surface, but unlike this N300 surface, these bridge droplets can efficiently slide along the surface. When these droplets slide away from the surface, it also carry away the tiny droplets underneath it. This efficiently sliding droplet can also provide a high heat transfer coefficient on this N100 surface. So we also quantify the dynamics on this condensation process on different surfaces. First is the liquid film velocity for among these 4-channel widths of these 3D hybrid surfaces. The liquid film velocity, we see that this N1300 surface has the highest liquid film velocity. This is because its channel width is largest, therefore it possesses the smallest flow resistance. Second, the number of the bridge droplets. At the low subcooling, we can see the bridge droplets happens on this N100, N300, and N600 surface. And this N100 surface has the largest number of the liquid bridge droplets. But as subcooling temperature increases, the liquid bridge droplet disappear on this N600 and N300 surface, but it maintains a large numbers at this N100 surface at medium and high subcooling temperatures. But as we seen in our previous slide, these bridge droplets can be efficiently removed is 6 times that on the superhydrophobic surface. This slide presents the heat transfer coefficient of the 3D hybrid surfaces compared to the silicon nanowire array and the plane hydrophilic surface. The solid line is again representing the theoretical prediction, which agree well with the hydrophilic plane surface. So as we can see, this silicon nanowire array again give a high heat transfer coefficient at low subcooling, but it decays significantly with subcooling temperature. This 3D hybrid surface can maintain a constant heat transfer coefficient from medium to high subcooling temperatures. Among these 3D hybrid surfaces, this N100 surface has the highest heat transfer coefficient because it has a large number of sliding droplets which can be efficiently removed by the gravity during the high subcooling temperature. So most importantly, by using this shorter nanowire, we can enhance heat transfer coefficient by 108% at high subcooling and also maintain a high heat transfer coefficient at high subcooling temperature. With that, I would like to summarize the result in this work. First, a stable condensation heat transfer was achieved at high subcooling on the 3D hybrid surface. Second, the efficient removal of these liquid droplets can enhance condensation on the 3D hybrid surface. This work was conducted by my student, Mr. Chen, and collaborated by Dr. Lo from National Zhongxian University. My second topic today is enhanced critical heat flux and heat transfer coefficient of poor boiling on a hybrid cover pillar array surface. First of all, the computing devices shift a lot from the decades, from this mainframe to workstation to personal computer to laptop to smartphones. As their size reduces, the power density increases. This trend especially surged during this AI era. The right-hand side figure shows the chip power density versus year. We can see that in year 2030, the hotspot power density on a chip can be as high as 2,000 watt per centimeter square. Okay, given this maximum power density at the hotspot as 2,000 watt per centimeter square, consider the only allowable temperature difference we can use is around 50 degrees C. Then we need a mechanism, heat transfer mechanism, with a heat transfer coefficient around 40 watt per centimeter square per Kelvin. So let's look at what we have. Here, this slide shows the heat transfer coefficient ranges by mechanism. First, for natural convection, using liquid as a cooling medium, the maximum heat transfer coefficient is around 0.1 with this unit. By using single-phase forced convection with liquid as the working fluid, the heat transfer coefficient maxima is around 1 to 10 watt per centimeter square per Kelvin. And only the phase change heat transfer can give us such a high heat transfer coefficient as required. Among the phase change heat transfer, poor boiling has a comparable heat transfer coefficient to flow boiling. And compared to flow boiling, poor boiling is easy to be implemented. Therefore, this study focused on pool boiling. This video shows a typical pool boiling process on a plain silicon surface. The liquid to vapor phase transition will carry a large amount of latent heat in a nearly constant temperature difference. The heat transfer rate from a pool boiling process can be obtained from this Newton's cooling law. On the left-hand side is the heat flux. Right-hand side is the heat transfer coefficient times the temperature difference between the heater surface and the pool at the saturation temperature. So because of this phase change heat transfer process, this pool boiling is a efficient heat removal mechanism. This figure shows a typical boiling curve for pool boiling. Before this onset of nucleation, point A in the figure, the heat transfer is dominated by natural convection. After onset of nucleation, vapor nucleation and vapor departure carry a large amount of phase change latent heat. Therefore, the heat transfer coefficient increases. The slope of the curve represents the heat transfer coefficient. But the efficient removal of the heat is limited by the critical heat flux of pool boiling. When the heat flux is larger than this critical heat flux, a huge temperature difference arises on the heater surface. This huge temperature rise will cause the heater damage and sets the upper limit of the efficient removal of heat transfer during the pool boiling process. And this heat flux is termed as the critical heat flux of pool boiling. Therefore, enhancing critical heat flux is important in pool boiling. The typical critical heat flux value on a plane surface is around 100 watts per centimeter square. This slide shows the state of art in pool boiling. In 2019, Zhang et al. Demonstrate this surface consists of porous structure with the channel array. This surface can give a very high critical heat flux around 800 watts per centimeter square. But the corresponding wall superheat is also very high, beyond 325 degrees C. This is beyond the practical application limit. And one thing to be noted, their structure is very high. The height of the porous structure is around 2.4 millimeters. Another study in 2021 also gave a very high critical heat flux, around 540 watts per centimeter square. But the wall superheat is still beyond 100 degrees C. And they claim that this vapor separation from the surface is the reason the surface can reach very high critical heat flux. This work from Kendall's group is the work showing the highest heat transfer coefficient in the literature with the value of 290 watts per centimeter square per Kelvin. The surface consists of these mini channels with nanostructures on the surface. I would like to go through our journey about pool boiling. I have been working on pool boiling since I was a student in Berkeley in 2009. At that time, we published a paper using copper nanowire and silicon nanowire to enhance pool boiling critical heat flux. Compared to the plain silicon, the critical heat flux is around 80 watts per centimeter square. These copper nanowire and silicon nanowire can give a critical heat flux over 200 watts per centimeter square. This is the first work demonstrate critical heat flux over 200 watts per centimeter square. Later on, we have been working on studying the mechanisms causing the critical heat flux on micro nanostructures. And we found that the critical heat flux on the micropillar array and also on the nanowire array are likely result from the hydrodynamic instability limit. And we have also studied emerging cooling using dielectrical fluid, Lombok 649 as the working fluid. By using the dielectrical fluid, it's more close to the practical application. And we found that the two-tier micro nanostructures can enhance both critical heat flux and heat transfer coefficient in emerging cooling. Our recent work published in 2024 used this 3D hybrid surface to enhance boiling heat transfer. The surface consists of taller hydrophobic area and shorter hydrophilic pillar array. The height difference between the hydrophobic pillar array and hydrophilic pillar array are among 100 to 175 micrometer. So we found that this 3D hybrid surface can enhance both critical heat flux and heat transfer coefficient. Compared to the plane surface, a 100% enhancement in critical heat flux and a 360% enhancement in HTC heat transfer coefficient are obtained on this 3D hybrid surface. So in summary of these literature results, we found that first, the work demonstrates very high critical heat flux using structures at or near the millimeter scale. But the underlying physics behind the high critical heat flux is still not clear. Most of these millimeter-sized structures fail to reach high heat transfer coefficient. And also the micro-nano structures can enhance critical heat flux and heat transfer coefficient in poor boiling. And from our previous work, we found that three-dimensional hybrid surfaces can enhance simultaneously critical heat flux and heat transfer coefficient. Therefore, this work focuses on applying this millimeter scale 3D hybrid copper pillar array with nanostructures to enhance boiling heat transfer, and also to study the mechanism that lead to the enhanced boiling heat transfer on the surface. Each figure shows the schematic of our 3D hybrid copper pillar array. The top of the pillar array are hydrophobic regions, and the rest area are hydrophilic with a narrow ring structure to enhance the wettability. The apparent contact angle on this surface is around 147 degrees. The height of pillars are 0.5, 1, and 1.5 millimeter. The pillar dimension is 0.5 by 0.5 millimeter square, and the gap between the pillars is also 0.5 millimeter. The control samples in this study include the untreated copper pillar array with the corresponding height, and the hydrophilic copper pillar array with the corresponding height, and also the plain copper surface and the hydrophilic copper surface with contact angle of 6 degrees and 70 degrees respectively. Here shows our experimental system for poor boiling. First, this heating element used 2 cartridge heaters to provide the heat. These cartridge heaters are connected to a power supply, and this heating element is surrounded by this glass fiber to prevent the heat loss. And we use thermocouples to obtain the temperature gradient along the copper block to get the heat flux to the surface. And this sample is bounded to the copper block by using the thermal interface material. And the edge of the sample is surrounded by epoxy to prevent the liquid leakage. And this 2 cartridge heater in this water tank is to maintain this pool at the saturation condition. And we use this high-speed camera to capture the bubble dynamics during the boiling process. First, this figure shows the boiling curve obtained on this untreated copper pillar array with a pillar height of 0.5, 1 millimeter, and 1.5 millimeter compared to the plain copper surface. On the plain copper surface, the critical heat flux is about 106 watt per centimeter square. The CHF on the 0.5 millimeter high pillar is around 170, and that on 1.5 millimeter is around 269, and on 2 millimeter array, 1.5 millimeter array is 219, and this one is 1 millimeter high. So one thing to be noted is that the critical heat flux does not monotonically increase with pillar height. Instead, this 1 millimeter pillar height has the highest critical heat flux. So to understand the mechanism causing the critical heat flux, we first estimate the critical heat flux using the fin theory, which consider the fin resistance limiting the critical heat flux of the surface. The heat flux from the pillar array can be obtained from this fin theory equation. On the right-hand side of the equation, N is the number of the pillars, H is the heat transfer coefficient, K is thermal conductivity, AC is the cross-sectional area of the pillar, and P is the perimeter. M is defined here. L is the pillar height, and theta base is the wall superheat. The total heat transfer rate from the surface is equal to the summation of the heat transfer rate from the pillar array plus the heat transfer rate from the base area. And then we can define the fin efficiency as this heat transfer rate divided by the maximum possible heat transfer rate by assuming the total area carry the same temperature as the highest temperature equal to the T base. This T infinite is the surrounding liquid temperature. Then using this fin theory, we can estimate the maximum heat flux from this plane surface. The equation shows that the maximum heat flux is equal to the critical heat flux on a plane surface times the area ratio between the pillar array and the plane surface times this fin efficiency. And the result for the pillar array with different heights are shown in this table and plot as the continuous curve in the right-hand side figure. The prediction shows that the fin theory give a critical heat flux increases with a pillar height and then becomes saturated at the taller pillars. But this result, this theoretical prediction cannot explain why this 1 millimeter high pillar has the maximum critical heat flux. So we further look at the critical heat flux not limited by the capillary limit. The capillary limit of the critical heat flux can be obtained by this equation. Assuming that vapor flow vertically out from the surface and liquid flow back to the surface vertically, then the critical heat flux due to capillary limit is equal to this capillary force balanced by the gravity force plus the viscous pressure force by liquid and viscous pressure force through vapor. Then using this equation, we can get the capillary limit of this surface and show as a solid curve in the left-hand side figure. This capillary limit decreases with increasing pillar height. This is because by increasing the pillar height, the flow resistance increases. At the same time, the critical heat flux limited by fin theory increases with pillar height. So we believe this maximum heat flux, maximum critical heat flux happens at 1 millimeter is due to this competing effect of this capillary limit and fin theory. This figure shows the boiling curve obtained on the hydrophilic copper pillar arrays compared to the hydrophilic plane surface. For the hydrophilic plane copper surface, the critical heat flux is around 150, and that for these hydrophilic pillar arrays are 275 for this 0.5 millimeter high, 374 for 1 millimeter high, and 1.5 millimeter, which critical heat flux is 347 watt per centimeter square. Again, we see that this 1 millimeter high pillar gives the highest critical heat flux. And we also look into the critical heat flux limited by the fin theory and capillary limit, and similar trends are observed. So we argue that this maximum critical heat flux at 1 millimeter is again limit and the fin theory. These figures compare the critical heat flux, the boiling curves obtained on this hybrid copper pillar array to the boiling curves obtained on the hydrophilic copper pillar array. Compare this hybrid copper pillar array to the hydrophilic copper pillar array. We can find that the critical heat flux are similar, but the heat transfer coefficient dramatically increases on this hybrid copper pillar array. The slope of this curve represents the heat transfer coefficient. So this 3D hybrid pillar array can give a similar critical heat flux, but a much higher heat transfer coefficient compared to the hybrid hydrophilic copper pillar array. So yeah, this slide shows this figure shows heat transfer coefficient versus heat flux. On this hybrid copper pillar array, we can obtain the heat transfer coefficient around 25, 28, and 31 for 0.5, 1 millimeter, and 1.5 millimeter high pillars. So the high heat transfer coefficient on this hybrid pillar array is because the large nucleation site density on the hybrid pillar array. The image shows the condensation dynamics taken on the hybrid pillar array and hydrophilic pillar array. We can see that on the hybrid pillar array, the nucleation site density is much higher, and also the bubble nucleation happens on the top of the pillars compared to the random nucleation on this hybrid hydrophilic pillar array. The right-hand side will quantify the nucleation site density among the three kite surfaces at three different heights, and we found that the hybrid pillar array gives the highest nucleation site density among the three kinds of the surfaces. So we believe that these large heat transfer coefficient on the hybrid pillar array surface are result from the high nucleation site density on the surfaces. With that, I would like to summarize the result from this part. First, the optimized critical heat flux obtained at 1 millimeter high copper pillar array result from the competing effect of fin resistance and the capillary limit. The hydrophilic pillar array can give the largest critical heat flux around 345, 344, and heat transfer coefficient around 9 watt per centimeter square. The hybrid pillar array can also demonstrate a very high critical heat flux around 368, but accompanied by a very large HTC around 28. The critical heat flux on this hybrid pillar array is 3.5 times on the plane copper surface, and the HTC on the hybrid pillar array is around 6 times on the plane copper surface. This work was conducted by the postdoc in my group, Dr. Somya Deep, and my student, Mr. Chen. At the end, I would like to acknowledge my members, my collaborators, funding support, and facility support. Thank you for your attention. I'm happy to answer any questions.
Yeah, thank you very much, Professor Lu. This is very advanced and very interesting subject. I invited for the participants. If you have any question, you can ask. Maybe the first question is from me, Professor Lu, if it's
Yes,
okay. So the result for the copper wire is very high, like 85% to more than 100% increase of his heat transfer coefficients. It's what the challenges the for the next steps. I think it's for the application in more device to apply this copper wire. What's the most challenging aspect that you face in this part? Thank you.
Sorry, because of the connection, I did not hear quite clearly of your question.
Oh yeah.
So
Yeah.
is the question about the condensation of poor boiling?
Yes, about the condensation of the first part. The first part.
Okay. The first part and the nanowire on the hydrophobic region are silicon nanowires. Okay, and they are
silicon
they are silicon nanowire. I think one of the challenges for this application is the fabrication of the samples. Yeah, fabrication of the samples because we need to control the hydrophobic area. Let me show you the schematic.
Okay.
Yeah, we need this area to be super hydrophobic, and this area in the channel region to be hydrophilic. I think the fabrication is one of the challenges in this sample design. Yeah.
So, what the common method to fabricate this? The
This
most
is
common method.
Yeah, this is a silicon nanowire, and the way we made this surface is by semiconductor manufacturing process. we use etching to get the nanowire array, and we use like a reactive ion etching to get the channels along with the nanowire array. So the fabrication process is a little bit complicated. And to have a more idea about the fabrication process, I think the details are shown in this paper. Yeah, yeah, yeah. Yeah, you can find all the details about fabrication in this paper. Yeah.
Thank you. Thank you. Um, and also maybe one more question. So,
Yes,
if you are looking for collaboration, what area you needed the most?
so I'm actually collaborating with professors from material science and engineering because some of the structures is very complicated, and we seek cooperations for professors from material science and engineering to provide us these sophisticated samples, and then we can study the heat transfer property of these samples. Yeah.
Mm.
So
Yeah, since in Indonesia maybe don't have the facility that advanced as yours,
yeah.
probably like the easiest way to collaborate in your expert in the transfer, probably using numeric method, like probably
Numerical. Yeah, yeah,
calculating
yeah. Yeah.
numerical. Is it possible, sir?
Yes, yes, it's definitely possible. Yeah, numerical simulation is also helpful, very helpful to elucidate, to explain the mechanisms during the condensation and boiling process. Yeah, but I know that it's very challenging to simulate the phase change process. Yeah, and that we are unable to give a good numerical simulation result. And it will be very helpful if there are some professors can provide us this kind of help. Yeah.
Okay, thank you very much. I also invite other participants. If you have any question, please, you can.
Yes, sir. I am.
Yeah.
Okay. Thanks for
Yes,
your
Imam.
presentation.
Pak Imam,
Okay. Can
Mr.
you hear me?
Imam Mutarom. Yeah, yeah, okay.
Okay.
Yeah, please state your question.
Okay. Thank you, Mr. Ming Chang Lu. I am Imam from State University of Malang. I'm very interested in your presentation. So, I have some question for you. In the industrial context, you highlighted hybrid wettability as promising strategy for boiling heat transfer. Could you please discuss the potential industrial application where this approach will be most impactful? And then, in addition, what challenge or limitation are faced in implementing three-dimensional hybrid micro or nanostructures on a large scale? Okay,
Yeah, yeah.
thank you.
Thank you for the question. Basically, I present two topics, including condensation and pool boiling today. And in both of these two topics, I use 3D hybrid surfaces. So that's because it's naturally a challenging process in phase change heat transfer to enhance both heat flux and heat transfer coefficient. So you know that during pool boiling, we need a hydrophobic surface to initiate double nucleation. But to maintain a high critical heat flux, we also need a hydrophilic surface. So the natural choice to enhance both critical heat flux and heat transfer coefficient then become using a hybrid surface. The surface consists of both hydrophobic area and hydrophilic area. The hydrophobic area can enhance nucleation. The hydrophilic area can enhance liquid supply. So this applies for both condensation and boiling process. And for condensation and boiling, they are widely used in industrial application. So in power plant, you have a boiler and you have a condenser. The heat transfer of boiler and condenser can limit overall heat efficiency of a power plant. Also, this pool boiling or emerging cooling are considered as a very promising approach for electronic cooling. As I mentioned in my motivation slide, the power density of the chip are now becomes very high, especially during this AI era. And the phase change heat transfer is considered as the only way to carry away such a huge amount of heat during this small area in these high power density chips. Yeah, so pool boiling or floor boiling is one of the very promising approach for electronic cooling for high power density chips. They are so that's the main application I can think about. Yeah, such as these cooling applications or in power plants. Yeah, I don't know whether I answer your questions or not. Yeah.
Okay, thank you, sir. I agree with you. For example, in power plant, improving boiling and condensation heat transfer can be significantly enhance the efficiency of heat exchangers. Yeah, I think I agree with you.
Thank you.
Thank you.
Okay, thank you very much. I think the time is up. I'm sure that a lot of participants still have many questions and also want to collaborate with Prof. Lu, but because time is limited, you can contact Prof. Lu if you have, and if we have more question. Is it okay if we contact
please.
you by
Feel free to
your
contact
email?
me.
Yeah. Okay. Okay. Thank you very much.
Thank you.
For the lecture, Prof. Lu. We really appreciate that you take your make your time in our conferences, and for the next for the administration process, I will contact you again in the email if you allow me.
Yes, please. Yeah.
Yeah.
Bye.
Yeah. Okay. You can stay, Prof. Lu, but if you have more another schedule, you can leave the conference.
Yes.
Thank you very much. Yeah. Thank you, sir.
Thank you.
So.
Nusantara. I'm student from Universitas Negeri Malang, Indonesia. In this presentation, I will talk to you about the presentation, the title, Mechanical Property of Cellulose Acetate Membrane made of Pineapple Waste Reinforcement by Hybrid Magnetite and Titanium Dioxide Nanoparticle. All right, next. Before I will presentation, there's several section I will introduction, literature review, material method, result and discussion, and conclusion. All right. First, introduction. Natural fiber composite can be an option in membrane manufacturing because environmental friendly and have a good mechanical property. In 2023, the Indonesian pineapple production exported 315,657.6 tons, making it a source of natural fiber. Pineapple waste can be processed into bacterial cellulose with the help of Acetobacter pseudomonas. The potential of bacterial cellulose obtained from the fermentation process is vast, including film, optical device, textile fiber, and membrane. Next, membrane are thin polymer layer used as a barrier in various industries. The disadvantages of BC membrane are their low performance, susceptibility to bubbling, tear resistant, and low heavy metal absorption capacity. Hopefully, with the addition of hybrid nanoparticle magnetite and titanium dioxide, the mechanical strength of the membrane can be improved. The next section is literature review. Pineapple is a source of natural fiber because it is easily obtained and support the Acetobacter pseudomonas with the advantage being environmental friendly, lightweight, and having good mechanical strength. Bacterial cellulose is known to have high mechanical strength and high degree of crystallinity, high purity, and significantly porosity. Magnetite and titanium dioxide hybrid nanoparticle are nanoscale composite material that possess the super paramagnetic properties, low toxicity, and high surface to volume ratio of magnetite, as well as the high mechanical strength, quick chemical stability, and non-toxicity of titanium dioxide. And next section, material and method. The material we use in this research is pineapple peel waste. The nanoparticle is magnetite nanoparticle and titanium dioxide nanoparticle from Sigma Aldrich. The method is first extraction and fermentation process of pineapple peel by adding 300 grams of pineapple peel, 2 liters of water, 150 grams of sugar, 5 grams of urea, pH 4.5, 20% Acetobacter pseudomonas, and then the fermentation process is for 10 days. Next process is alkalization treatment. The 1% NaOH solution for 2 hours at 90 degrees Celsius, blended with a high speed blender for 5 minutes, and then homogenized for 5 cycles. And acylation procedure with 5 gram nanocellulose, glacial acetic acid, sulfuric acid, acetic anhydride, and followed by 4-hour reaction. To find of cellulose acetate was then added 1% CO and then magnet with variable 0.25%, 0.5%, 0.75%, and 1%. The result from this research is enriched for bacterial cellulose acetate membrane in pure what A as a smooth morphology small pores, and then with the addition of 0.25% and 0.5% magnetite to the bacterial cellulose acetate titanium dioxide membrane in picture B and C make the surface like straw to magnetite TiO. I'm sorry, I mean titanium dioxide aggregation at magnetite content of 0.75% and 1% in tier B and E. Like agglomeration occurs due to small particle size, magnetic properties, and high nanoparticle concentration, which inhibits entry into the BCA network. Nanoparticle aggregation reduces the interaction between magnetite and titanium dioxide and the BCA metric or bacterial cellulose acetate metric, thereby affecting the morphology and property of the membrane. Titanium dioxide appear white, spherical, and easily aggregates as found by Yanuhar et al. At 2022. Magnetite is spherical in shape, measuring approximately 8 to 11 nanometer with a distinctive black color, and also shows a tendency to aggregate. This agglomeration is caused by the very small particle size, like surface area and cohesive properties of the nanoparticle. So, in discussion, the contour membrane show a smooth and consistent increase in force, indicating uniform material behavior when subject to axial loading. The end of titanium dioxide and magnetite nanoparticle in figure B began to cause slight irregularities in the force strength curve, indicates change in internal structure and load distribution. At magnetite concentration above 0.25%, figure C and E, the force strength curve become increasingly wavy due to nanoparticle agglomeration, which creates stress concentration point and disturb uniform membrane deformation. Then the tensile strength of the membrane increased with the addition of magnetite titanium dioxide nanoparticle, reaching a maximum value of 73.56 megapascal at the concentration of 0.75%. Average tensile strength control 0.25%, 0.5%, and 0.75%, and last 1% is 41.97 megapascal, 40.54 megapascal, 69.3 megapascal, 73.56 megapascal, and then 39.98 megapascal. One-way ANOVA analysis showed the addition of magnetite had a significant effect on tensile strength, with the value, the N value 4 and alpha value is 0.05. Kipos hook is 0.5% and the 0.75% were not significantly different from each other, but were significantly different from other treatment. The highest tensile strength was associated with more uniform nanoparticle dispersion with the minimal agglomeration at the membrane, while a concentration of 1% showed a high agglomeration and the low tensile strength. The last section is conclusion. Hybrid reinforcement of bacterial cellulose acetate membrane was successfully with the addition of magnetite titanium dioxide nanoparticle. Same so that the membrane surface became rugged and more agglomerated at concentration of 0.75 to 1%. The highest tensile strength was achieved at 0.75%. The value is 73.56 megapascal. The ANOVA with the PEP value is 0.05. Confirm the significant effect of nanoparticle on tensile strength. Also, the EHD did not find significant difference between concentration. the acknowledgement. Many thanks to the Department of Mechanical and Industrial Engineering, Universitas Negeri Malang, for funding this presentation in this seminar.
Yeah, thank you, Mr. Fajar.
Thank you, sir.
It's a very interesting subject. Please, for the other presenter or other participants, you can ask a question if you have one, please. Is there any question? No? Okay. Because there's no question, probably I will ask one for Mr. Fajar. Mr. Fajar, I know that pineapple is one of the good resource of fiber, but can you give us other source that can be applied other than pineapple fiber here? Thank you.
All right. I will try to answer the question. Any other source can be used as bacterial cellulose is so many like in commercial like a coconut that can be used as bacterial cellulose. The apple peel can be used, and then there are sargassum. There's there's except sargassum, there's I think the organic have glucose in there can be used as bacterial cellulose starter. So I think that's
Thank you. So, your method is, can it be used for other than pineapple? So, for the coconut example, or yeah, and other organic matter. So this method can be used
yes,
outside of
course.
the pineapple.
Of course, but the result will be different. Usually the result of the thickness of the bacterial cellulose acetate will be different every material.
Okay, so I think it's very interesting to study other than, because sometimes pineapple the supply chain is not that established, so sometimes it's abundant, sometimes it's very rare to find pineapple, and so yeah, I think it's a good method if you can apply it to another materials. Yes. Thank you, Mr. Fajar,
Thank you
for the
so much.
presentation. So we will move on to the next presenter, which is Imam Mutarom, with the title of Casting Defect Analysis using AI-based micro and macro photos in ALSE alloy, aluminum silicon alloy, metal casting with variation of local Bangkalan clay binder. So, Mr. Imam Mutaram, how are you?
I'm fine, good, thank you.
So you can start the presentation. The time is 15 minutes, around 15 minutes, and 5 minutes for question and answer session. So time and place is yours.
Okay, thank you. Let me share screen first. Okay, can you see my screen?
Yes, the screen is good, the sound is
Oh,
good, so you're good to
okay,
go.
okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, thank you, Mr. Latif Fikri, for my time. Good morning, everyone, and may peace be upon us all. Distinguished speakers, researchers, academics, and estimate participants, let us express our gratitude to Allah Subhanahu wa Ta'ala, for it is by His grace and that we are able to gather today in this scientific forum. On this occasion, I will present material on casting defect analysis using artificial intelligence-based micro and macro photos on aluminum silicon alloy metal casting with variation of local Bangkalan clay binder. And it is my hope that this presentation will serve as valuable basis for our discussion and contribute to meaningful insight for all of us. Okay. And then the next, the background is sand casting actually still dominated 70% of the manufacturing industry. And then the quality of the casting influenced by the sand and the binding material. Then bentonite are the most common, but a local alternative, Bangkalan clay, has potential. And then the challenges is traditional defect detection method, visual radiography or metallographic are still limited, subjective, slow, and difficult to detect micro defect. And then the next, you can see the table. Based on the table, the characteristic of local clay Bangkalan have significant similarities with binders in general. The research revealed that the higher percentage of local clay binders in Bangkalan. You can see the table. The magnesium has concentration with 6.0, and then calcium with concentration 92.181%. Then ferro or iron with concentration with 0.24, and then copper or cuprum with concentration 0.07, and then strontium with concentration 0.27, and then ytterbium with concentration 0.56. Okay, that's all. Based on the table, the characteristic of local Bangkalan clay binder have significant similarities with binders in general. So, by research by Saifullah also showed the variation in the use of binders, local Bangkalan clay, bentonite, and fly ash at 99% result in different mode quality. Okay, and the next, the research gap of this of my research is the one previous research focused on mechanical properties. Yeah, nonetheless, most previous research has still focused on the relationship of binding material variation to the mechanical properties of metal, such as tensile strength, hardness, and macro defect. There has been no study that has in-depth evaluated the method of defection and analysis of casting defect. In fact, defect detection is a crucial aspect in ensuring the quality of casting result. And then the analysis method is not much has been explored in artificial intelligence-based metal defect detection because as digital-based manufacturing, AI has capabilities in imaging process, pattern recognition, and data-driven learning to detect casting defect faster, more accurately, and consistently. So, artificial intelligence validation can also data-driven learning detect casting defect faster. Yeah, like that. And then the research novelty is integration of artificial intelligence like ChatGPT Pro plus vision analysis in the evaluation of casting defect. So this is more novelty for the before of research. The next is research objective. The analysis of the effect of fastener variation, 6%, 9%, 12%, on the quality of aluminum silicon cast. And then to identify casting defect, drop micro and macro photos, and then to integrate artificial intelligence for defect classification like porosity, crack, inclusion, and et al. And then to compare artificial intelligence result with expert manual evaluation. The experimental methodology, this study use experimental design with one-shot case study approach, where a group of sample is given a specific treatment and the results are observed. The study involved 3 independent variables and 2 bound variables. The 3 variables consist of variation in the percentage of local clay binder in Bangkalan, namely 6%, 9%, and 12%, while the bound variable was casting defect seen in micro and macro photos. The control variable in this study include wet sand, mold with mixed composition, 5% water, 0.5% bentonite, and aluminum silicon or ALSC derived from used piston. There are 3 treatments carried out this study. The first, aluminum silicon metal casting with sand molding using mixture 88.5% silica sand, 5% water, 6% local Bangkalan clay, and 0.5% bentonite. And then aluminum silicon metal casting with sand molding use mixture 85.5% silica sand, 5% water, 9% local Bangkalan clay, and 0.5% bentonite. And then the third is aluminum silicon metal casting with sand molding using mixture 82.5% silica sand, and then 5% water, and then 12% local Bangkalan clay, and then 0.5% bentonite. If they duplicate in the form relationship, you can show the image. The research design, if we see the design of research, start with preparation of silica water, local Bangkalan clay, 6%, 9%, and 12%, and then mixing, and then molding making, and then metal melting or peleburan logam, metal casting, kemudian pengecoran logam, and then preparation of micro and macro photo specimen, and then metal casting, metal defect testing based on micro photos using artificial intelligence, and then macro photos using artificial intelligence, and then data analyze, conclusion, and finish. Okay, and the result, defect test based on micro metal photos. You can see the picture. A micro photo specimen with binding variation of 6% local Bangkalan clay and 0.5% bentonite. You can see the one of white, that is aluminium. Then the red is silicon, and then the yellow is aluminum silicon or the binders, yeah, like that. Then the specimen with a binding percentage of 6% show a more heterogeneous distribution of metal grains with relatively large and uneven grain size. Metallurgical, this can be attributed to a non-uniform cooling rate, thus inhibiting nucleation and encouraging the growth of coarser grain. This condition increased that tendency for porosity to form due to gas entrapment during solidification. In addition, the low level of binders reduce the mechanical strength of the sand mold, which can lead to mold deformation when receiving molten metal pressure and giving rise to crack. The result, the defect test based on micro metal photos. The next is B with variation of 9% local Bangladesh clay and 0.5% bentonite. You can see the white is aluminium, the red is silicon, and the yellow is aluminium silicon. In this specimen with binding of variation of 9% local Bangladesh clay, distribution of metal grain appears to be more uniform than in previous specimen. The increased fastener improved the permeability of the sand mold, thereby aiding gas release, reducing porosity potential. And then from the point of the view solidification kinetics, a higher binding rate stabilize the rate of heat transfer, resulting in a smoother distribution of the grains. However, small cracks remain visible due to the thermal expansion mismatch between the molten metal and the mold. This is aligned with the literature report that although increase the fastener improve the homogeneity of microstructure, the thermal stability of the mold must still be controlled in order for cracking to minimize. The next is 12% local Bangladesh clay with 0.5 bentonite. You can see the white is aluminium, red is silicon, and then the yellow is aluminium silicon. With specimen of 12% binding, exhibit more uniform metal grains with more controlled solidification indication. The increase in the fastener helps to strengthen the sand mold so that the internal pressure of the molten metal is better able to be withheld, reducing the risk of cracking. However, inclusion were found in some areas, possibly due to overbonding that increased the amount of non-metallic residues in the mold. Research show that the use of axis binders in the sand molds has the potential to result in the inclusion of oxides and then foreign particle in gas result. Thus, there is a trade-off. Higher binder level increase grain homogeneity and decrease porosity, but risk introducing inclusion defect that can degrade material toughness. And then this is a macro photos of metal surface. You can see the A micro photo specimen with binding variation of 6% local Bangladesh clay and 0.5% bentonite. The specimen 6% binding have many small cavities in the form pinholes. The phenomenon can be explained thermodynamically as a result of a gas pressure greater than the mold ability to release gases. Mold with weak bonds tend to be non-uniform porous, so gas can be trapped in the molten metal and form with pinholes. In addition to open grain structure is also visible, which indicate cooling too fast, so that the bonding between the grain is not perfect. This condition weakens the mechanical properties of the metal due to the presence of potential crack path. And the B is variation of 9% local Bangladesh clay. Yeah, in specimen 9% fastener, the number of pinhole is noticeably reduced. Increased binder is level, increase the rigidity of the mold, resulting in a more even distribution of thermal stress and reducing structural defects. However, small crack remain visible, which signifies that despite better mold permeability, temperature control, and cooling gradient remain determining factor for surface quality. From the perspective of material mechanics, this condition result in a compromise, reduced macro defect, but still susceptible to local thermal stress. The next, the last one, microphotos specimen with binding variation 12% local particle nuclei and 0.5 bentonite. This specimen with 12% binding show the best result with the least number of pinhole and denser grain structure. Improve the stability of the sand mold, allow for more controlled freezing, thus improving grain distribution. However, the presence of some small pores and non-metallic inclusion remains detected. This supports the result of recent studies that although increase fastener strengthen mold and reduce gas defect. To hide a number of fasteners can increase the risk of inclusion defect that actually lower final mechanical performance. Therefore, then the binding level need to be optimized in order to achieve a balance between porosity reduction and inclusion defect minimization. And then the conclusion is, and recommendation is an increase in the percentage of binder has a significant effect to homogeneity of metal grain structure, and the reduction of surface defect at 6% binders, porosity defect and pinhole are more dominant due to non-uniform solidification. The 9% variation improve that the grain distribution and reduce the amount of porosity even though small crack are still visible. Meanwhile, the 12% binder produce the most uniform metal grain with minimal defect despite the potential for inclusion due to overbonding. Thus, fastener variation of 9 to 12% can be considered more optimal, with 12% showing the best result. While artificial intelligence integration has been shown to improve the accuracy and efficiency of casting defect analysis. Like that. Okay, thanks for your attention. I think enough. I will now return to for the moderator. Thank you.
Yeah, thank you very much for the presentation, Mr. Imam. Maybe I will ask quick question. How you measure the improvement of the AI by using AI? Yeah, thank you.
Yeah. Thank you, Mr. Atif. I think artificial intelligence was used in this research because conventional defect analysis method, which really on manual observation under a microscope, are often time consuming, subjective, and prone to human error. By integrating artificial intelligence, particularly image-based classification, we are able to process metallographic image more quickly and consistently. The artificial model can recognize specific defect patterns, such as porosity, pinholes, cracks, and inclusion with higher accuracy. This not only reduces the time required for evaluation, but also enhance the reliability of the result. Furthermore, AI enables large datasets of image to be analyzed systematically, which is very difficult to achieve through manual method. Therefore, AI contribute to both efficiency and precision in casting defect analysis, making it is highly beneficial for industrial application where quality control must be performed on large scale. I think enough, Mr.
Okay, thank you very much for the answer. Is there any more question? If it's not, we will continue to the next presentation. The next presentation is by Chi Kai Chen, Yu Wen Chen, and Hong Yun Wu. Is the presenter here? Chi Kai Chen. I think it's not here yet. So we move on to the next one. Is Bahrul Ilmi, Supriyanto, Tulus Burhanuddin, Sitorus, Ikhwan Shah Isra Nuri, and Taufik bin Nur. I think it will be present by Bahrul Ilmi. Is it correct?
Yes, Mr. Atif. Thank you for the
Uh,
time and
yeah.
opportunity.
Before we start, I will introduce that the presentation is titled is Effect of Titanium Carbide, TIC, particles on characteristic of polymer matrix composite, PMC, synthesized by reflux method. So, without further ado, please give your speech. Time is yours. It's 15 minutes for the presentation and approximately 5 minutes for question and answer session. Thank you.
Check. Thank you, Mr. Atif. Thank you for the time and the opportunity. Let me introduce myself. My name is Bahrul Ilmi. I'm from the University of North Sumatra. It's an honor for me to the present or the latest research with the title Effect of Titanium Carbide Particle on the Characteristic of Polymer Metal Composite Synthesis by the reflux method. Introduction in this research, one, the polymer are the increasingly used in the engineering and hydraulic technology application. Polymer metal composite can be tailored with the ceramic additive, it's silicon carbide, aluminum oxide, boron nitride, aluminum nitride, add shaders to the enhance mechanical and physical properties such as tensile strength, toughness, and thermal stability. Polypropylene is the attractive due to its lightweight, high usage, and favorable mechanical properties. Reinforcement with the TIC improves addition, toughness, possibility, and adds benefits like thermal stability and resistance to fatigue and corrosion. Various fabrication technique exist for the polymer metric composite, e.g. hand layup, injection molding, resin transfer machine, at shaders. But the reflux method is the highlight as the simple, cost-effective, and capable of the production control and of structure with the tunable size, morphology, and the crystallinity. Lightweight polymer composite can enhance vortex turbine efficiency. Prior study saw power output varies with the implant material. It's steel, aluminum, acrylic, polylactic acid. This study investigates polypropylene TIC composite synthesis via reflux to improve physical and mechanical properties for the vortex turbine impeller, hypothesizing that the higher TIC content increase tensile strength, toughness, and power efficiency vortex turbine. Next method in this research, this one preparation of a tool and the material. Second, the homogenization polypropylene TIC with the reflux method. 3, sample print with the hot press machine. 4, the mechanical characteristic for the PMC, PP, and TIC. Structural analysis, and finally fracture morphology and ADS mapping PP and TIC. And then result for the physical and mechanical properties. This one, density of the PMC TIC with different TIC composition is presented in the table 1. Increasing TIC tend to increase the density of the PMC. Next, the tensile strength result. So in the figure 2, Higgins tensile strength 33 megapascal was obtained with the 95% and 5% PMC TIC ratio, as shown in figure 2. Next, result for the flexural strength result, so that the figure 3, Higgins flexural stress 64 megapascal of the PMC TIC within the composition 93% PP and the 7% TIC was the obtained. And the impact isot chart show in the figure 4 that the presence of the TIC within the polypropylene matrix brings a different effect on the impact strength. The highest impact strength 31 kilojoule per square meter was the attained for the 9% TIC. Next, the extended pattern for the PMC TIC shown in the figure 5. The addition of the TIC particle bring a slight change in the crystalline degree and size. The particle content increase tend to increase crystalline degree and size. This is based on the previous finding that state that the peak shift or the change in the crystallographic plane increase the size of crystalline in the composite. Next, fracture morphology. So in figure 6, morphology of the PMC TIC composite is the clearly observed that the fracture area exhibits ductile fracture mechanism. As indicated by dimple formation, the increase in the TIC particle content lead to the formation of the void within the polypropylene matrix, which affect the mechanical properties and the fracture behavior. Small void are the observed in the fracture area of the 7% TIC composite. See figure 6b. This condition is believed to enhance the stability and flexural performance of the material. Next, result from the scanning electron microscopy and the electric dispersion spectroscopy mapping. So in the figure 7, the result of the mapping of the TNC-PFC composite matrix and the filler element examined at 2 different points. The distribution of the element carbon and the titanium is also illustrated. Especially the distribution of carbon is shown in the figure 7C and will the distribution of titanium presented in the figure 7D. Particle distribution is quite good and even, although for titanium there is still a slight clamping at the same point and area. Conclusion: this research, the addition of the TIC particle into polypropylene matrix successful synthesis by the reflux method, and the mechanical properties were obtained by different method, in which the addition 5% and the 7% TIC result in the higher tensile and the flexural strength respectively, and the higher impact stand 31 kJ per square meter was obtained with the 9 TIC. A small void size was observed with the addition 7% TIC. Furthermore, the addition of the TIC also influenced the crystallinity and the crystal size of PMC material, and also the particle distribution is quite good and even, although for the titanium there is still a slight clumping at some point area. That's all presentation for me. Thank you for attention.
Yeah, thank you very much, Mr. Badrul. Maybe from the other presenter or participants have any question, please feel free to give a question. Maybe one from me. Its application is for turbine, is it correct?
Yes, application for the vortex turbine impeller, make impeller for turbine vortex.
Yeah. Any other ideas? What the application other than turbine?
Other application for damping for vibration, high vibration machine, or
Yeah, that's need a high impact. Is it correct? Yeah.
yes.
Any okay. Any other question? If not, okay. If there's no other question, we will have a break for 5 minutes. So and then we will continue the presentation to the next presenter. Thank you. Okay, maybe Ilona still have a problem. We can go for the next presenter is Supriyanto. Mr. Supriyanto,
Yes,
can you
Mr.
hear us?
Fikri. Yes, I can hear you
Yeah,
clearly.
thank you. Yeah, thank you. How are you, sir?
Fine, Mr. Fikri.
Yeah, Mr. Supriyanto will present with the title of the characteristics of the copper nickel ferro X MO alloys. So this is an alloy synthesized by powder metallurgy.
Yes.
So the presentation time is 15 minutes with 5 minutes of answer and questions. So you the time and place is yours, sir. Thank you.
Baik, thank you very much for the time, Mr. Fikri, as a moderator. This Isefmi 2025. Right, I will present our research topic entitled "The Characteristic of Copper Nickel Iron X Molybdenum Synthesized by Using the Powder Metallurgy Technique." My name is Supriyanto from University of Sumatera Utara in Indonesia. This topic based on our experience uh, in our workshop. Actually, we know CU-based alloy are widely used as electrode component due to their high electrical conductivity, but these components have a big problem in practically because these alloy have low wear resistance and low mechanical properties. There is many technique to improve the mechanical properties of this alloy. The first one is we can added some element, for example, Cu with nickel, Cu with iron, or Cu with molybdenum. When we added this element, it will enhance the strength, thermal stability, and erosion resistance. Particularly for molybdenum, this element is very effective to improve the hardness, strength, and hardness. Although this element can reduce the ductility of the alloy. In our research, actually, there is many study discuss about geonickel based alloy system, but study on nickel iron alloy with molybdenum addition is still limited. So the aim of this study to investigate the effect of varying molybdenum contents on microstructure development, mechanical properties, and electrical conductivity of nickel iron molybdenum alloy. This is our material methods. We use the powder base with high purity condition above the 90-10 purity of the powder. Synthesis by powder metallurgy with mixing. We use the mixing process by using mixer type and compaction at 250 MPa and sintering temperature at 770 degrees Celsius. And we try to get some data or characters of the sintered material by using optical ACM, ACM EDS, and mechanical properties like hardness, compressive strength, and electrical conductivities. Table 1 shows us about the composition of the model CU-based alloy. We can see in the table 1, we try to add molybdenum from 0 to 3% of molybdenum. We can see this is the sample with different composition. And then we use the CU nickel ratio with 90 to 10% for CU and nickel respectively. This is the result the result of our study. Figure 1 show us about microstructure of the sintered alloy by using optical microscope. We can see the figure 1A show us the microstructure alloy without molybdenum, and B, C, and D show us about the microstructure with 1, 2, and 3% molybdenum. From the microstructure, it is clearly we can observe that the microstructure consists of porosity between the microstructure identified by the dark area. We can see this is a more larger dark area we found when we increase the molybdenum. And so there is any gray, green, yeah, light green area, and so yellow area. And the second one in this image, figure 2 show us about elemental distribution of the each of element. We obtain this image by using SEM EDS methods. We can see this is the Cu nickel rich ore. This is a this area, like I saw with this cursor, consists of Cu rich. So this the green, it is nickel, and so this is the red, yeah, the red area. This similar to the molybdenum particle. From this image, we can understand that the addition of the molybdenum up to 3%. When we see molybdenum with 3%, it is believed that the molybdenum, it is hardly to dissolve into the matrix. Most of the molybdenum tend to segregated in the grain boundary of the microstructure, because we know we use the sintering temperature at 770 Celsius, and molybdenum have highest melting temperature more than 2000 degrees Celsius. And this one is the microstructure of model alloy with 3 molybdenum. This is EDS point near the grain boundary, and it is clear from EDS point we obtain the element, this area consists of Cu as a matrix, and nickel and molybdenum, and also oxygen. Molybdenum, as I explained before, molybdenum tend to disperse or segregate in the grain boundary, and also oxygens. This is a density of model alloy. The increase of the molybdenum content tend to increase the density, and also the hardness of material. And then this is a compressive test result. It is clearly when we increase the molybdenum content from 0 to 3% of molybdenum, we often increase the, I think increase the hardness, but not significantly. In this current study, we obtain. And the compressive strength tend to increase only 1% molybdenum and slightly decrease when increase the molybdenum content. I think it is correlated with the dispersion of molybdenum. We know it is hardly to obtain a homogeneous distribution of the particle molybdenum by using the Fay mixer. I think it is the problem in this reason. So maybe in the near future, the better mixing method can be used to improve distribution of the molybdenum particles. And then this is the fracture morphology of the alloy. We in this image figure 7, it is the microstructure or fracture morphologies of the model alloy without the molybdenum. We can see this is, we observe some porosity and then intergranular crack observed in fracture area, and also this is I think this is a porosity less than 2 micron in size, I think. And then the second one is the image of the fracture morphology of CU-based alloy with 3% molybdenum. The fracture morphology, it is not very different, but porosity still observed in microstructure, but in fracture also we observe there is any transgranular patch formed between the fracture area. So in our current study, we found that with molybdenum we found mixed fracture, ductile and transgranular cracking. So it is clear molybdenum improve fracture toughness and prevent abnormal grain growth. And the last one is the electrical characterization. We can see when we added the molybdenum, it tend to reduce the electrical properties of the CU-based alloy. We know the electrical properties CU is the higher below the silver, but when we added more element or contaminant, it causes the electrical conductivity tend to reduce. When we can see from the image, when zero molybdenum, we get about 75% EICS of conductivity, but this value tend to reduce up to 65% EICS when we added 3% molybdenum. So there is many factors influence this electrical characteristics, but we believe due to the molybdenum have lower electrical conductivity, it is the main cause of the electrical characteristic to be low. Beside the element molybdenum element, lattice distortion, impurity, porosity, we believe influence or can contribute to reduce the electrical conductivity. And then the opposite is resistivity. When conductivity remain to be low and resistivity to be high or increased. Yes, this is the electrical characterization. And the last one is conclusion. From the data, we can make some conclusion. The first one is when we add a molybdenum into CU nickel ion, it is significantly improve hardness, but a slightly increase of the compressive strength up to 1% and then slightly decrease when we add molybdenum about 3%. The second one, strength improvement are due to better densification, and of course dispersion strengthening is very important to improve the mechanical properties of the Cu nickel iron-based alloy. And the third, fracture behavior, a mixture of ductile intergranular fracture with dimple and microscope observed. And the last one is the electrical conductivity decreased from 75% until 65%. Yes. Okay, I think that's all my presentation. Thank you very much for your attention.
Yeah, thank you for the presentation, Mr. Supriyanto. Is there any question for the attendant or participants or other presenter, please? Maybe one from me, Mr. Supriyanto. You measure both of the electrical properties and also the mechanical properties. Is there any needed application that need both of the mechanical and also electrical side? Thank you.
Baik, thank you, Mr. Vicky. Yes, yes, there is we have a problem in our workshop because in practically when we use the electric discharge machine, we have one of important component like electrode. So in workshop, that we use the Cu-based alloy as electrode component. We have a problem with this electrode because sometimes we find the electrode to be wear and sometimes electrode to be fractured in the tip area. This is a problem. So because we believe Cu-based electrode have a lower strength, so it is our problem. So we try to improve the strength of the electrode, but the problem is when we improve the strength of electrode, the electrical conductivity to be lower, decrease. It is a problem. So we try to find a compromise between the mechanical properties and electrical properties. Of course, when the electrical conductivity decrease, it will influence the cutting speed. I think it is that's my answer, Mr. Fikri.
Yeah, thank you very much. It's very
Thank
clear.
you.
Is there any more question, please? No, if not, thank you very much, Mr. Supriyanto, for the presentation. We will move on to the next presenter. I will ask for Chi Kai Chen. Is it here, Chi Kai Chen? I think it's not here, Chi Kai Chen. Then Rediarsa Dharma Bintara. Mr. Reddy? Are you with us, Mr. Reddy? Mr. Reddy? I think Mr. Reddy is not with us. I will call out for Ilona Joan Manuela.
Yes,
Ilona?
I am present.
Yeah, okay. Ilona Joan will present with the title of the computational investigation of Mont Morilonate based biomaterial for sustainable bone implant application. DFT insight into calcium and phosphate absorption. Is it true?
Yes, it's true.
Yeah. Okay. How are you, Ilona?
I'm very good, thank you.
Yeah. It's very nice for you to join us. So the presentation time is 15 minutes with 5 minutes of the Q&A session. So I will give the time and place to you. It's yours. Thank you.
Okay, I will share my screen. Okay, I'm going to start. So good afternoon, Isefmi committee and also speakers, presenters, and participants on today's event. In advance, I'm going to introduce myself. My name is Ilona John Manuela from Bandung Institute of Technology. And at this time, I'm going to present my work on the computational investigation of monmorillonite clay for sustainable bone implant applications using insights of density functional theory. So for bone implant, an ideal material needs more than just mechanical strength. It requires biocompatibility, mechanical stability, and bioactivity, which is the ability to interact with the body's biological components, specifically key ions like calcium and phosphate, which are essential for bone growth. So the goal is to develop sustainable materials that can actively recruit these ions to promote bone healing, moving beyond traditional implants. So why did we choose morillonite clay in the beginning for our research? Because it is naturally abundant, low cost, sustainable, and it has high cation exchange capacity, meaning we can do some modifications and insert a cation and exchange can happen. So towards our research goal, we do this so it can make some certain functions that we want. As previous studies have shown, so this MMT enhanced composite, it can improve bone activity, and the clay itself can absorb biological ions. So our hypothesis, the hypothesis that we made, was that by modifying it with calcium atom, we could create a surface that effectively absorb phosphate ions, forming a bioactive platform for bone generation. So this led us to a central question, which is phosphate absorption type of CAMMT thermodynamically favorable and electronically significant? Is there any changes that is significantly can be seen? And our objectives are, we are going to calculate, first we are going to make the model of the atomic structure and then calculate the absorption energy, and then we do some analyzations, which is the electronic structure changes that we can see from the band gap. To answer this, we use a density functional theory, which is a first principle quantum mechanical method as implemented in the VASP software. It is a standard software in computational material science. So we started off with a pristine clay model, introduce a magnesium and aluminum atom to create a negative charge, and then added calcium as an interlayer atom to balance it, creating our CAMMT model. And then we make also a phosphate molecule to finally we put in the system and it can be absorbed and we can analyze from the optimization. So these are the three models that we have made. So our first key result was from the absorption energy. So after calculating from each of the models that have been made before, so the models are made and then optimization is done, we then see the numbers of the total energy in electron volts. We calculated a value of minus 0.4377 electron volts. This negative value confirms that the process is thermodynamically favorable and spontaneous. This suggests a stable yet potentially reversible binding, which is ideal for a dynamic biological environment where ion exchange is critical. So this is the equation that we use to measure the adsorption energy. Now, how phosphate binds, where we can see from the figure below, a new bond is formed. So looking at this geometry, we see how it binds. After optimization of both of the model, this is the before and the after, so we can see that a new chemical bond forms between the surface calcium, the surface of the montmorillonite from the calcium atom, and an oxygen atom from the phosphate. So this isn't just weak physical absorption of phosphate from the biological system, for example, in human blood and montmorillonite. There is a stronger coordination interaction because we can see that a chemical bond is formed. This bond acts as an anchor, stably attaching the phosphate molecule to the surface of montmorillonite. This finding is consistent also with other DFT studies on similar systems. So another finding is about the electronic and conductivity of the system. Phosphate absorption enhances surface conductivity. Also, here is the DOS graph, density of states total of two systems. The top blue one is the after absorption, there is a phosphate molecule attached, and before is the only montmorillonite system. We can see that before, the pristine clay is a good insulator with a large band gap of 2.7 electron volts. But after the phosphate is absorbed on the montmorillonite and the system is measured, this gap narrows significantly to about 1.2 electron volts. So what does it mean and why does it matter? The smaller band gap means higher electrical conductivity. And as recent research shows, this enhanced conductivity can regulate bone immune signaling, and it is a key principle of self-powered biomaterials, making the surface that we have made is potentially electroactive. So next, from calculation to application. What does this mean after we have seen the results? What can we applicate this to? So we have a material that offers sustainable bioactivity by recruiting essential ions and also enhanced conductivity that could facilitate electron-assisted healing process. Because the biomaterial that I'm going to make is correlated to healing, where it is used in medical or health industries. So this creates a synergy, which is by combining the sustainability of natural clay with advanced functionality through a surface engineering. So in conclusion, our DFT simulation confirmed that calcium-modified montmorillonite is a promising, sustainable platform for bone implants. And some future works that we are planning to do. First, we are going to model more complex conditions because the human body and biological system contains more complex components like blood, protein, and other molecules. So we plan to make a more complex system. So the biomaterial that we design can be more accurate. And then also the second is to investigate the protein absorption because protein is one of the most abundant component in the human body. And most importantly, pursue experimental validation to confirm these computational predictions. By experimental validation, we mean to do lab work on the montmorillonite clay and do some material designs to really use it and do application on the health industry. And I would like to thank my supervisor and also co-author, Ibu Triati Dewi Kesanawungu, for her invaluable guidance and also doing the research along with me, and also our faculty, the Mathematics and Natural Science, and also PPMI grant for their support um, towards my research and also joining this conference. So thank you for your attention.
Yeah, thank you, Ilona Joan, for the insight. It's very interesting. Maybe I would like to ask the first question first. So density functional theorem is I really like this subject, but it's very hard to validate. Do you have any plans like what the best way to validate the result of the DFT?
Mm.
Or can you give us insight what is the best way to validate the result of the DFT? Thank you.
Thank you for the question. So, usually in computational science research, there are two ways to validate uh, the data or the result that we have got. First is to compare it with other research and other scientific findings and parameters. So, from literatures and the research before, comparing it, is it the same or is it different? And the second way is to do lab work, experimental lab work. For example, in my case, is really using the Montmorillonite clay, take it from nature and process it, and also using it as a biomaterial. For example, giving it a certain condition and then measuring with some instruments, some physical or chemistry, so physical chemistry instruments, and then get the data and also comparing it with the computational results. So maybe that is the insight that I can give you by comparing it with other computational data research and also doing some lab work.
Yeah, thank you. But maybe one one more question, if it's okay.
Yes, can.
Uh, DFT time step is very short, like picoseconds. Is it
Yes.
correct? Picoseconds. But the lab work is usually you can measure it in seconds. So how to manage that you using some DFT data of picosecond and you compare it to the lab work which measure in second or minutes.
Oh,
It's a bit confusing for maybe for me. And yeah, thank you.
I
Can you
see.
answer that?
Yes. Maybe I will start off with, so usually we do the FT to design a material. So the first step, like designing and some creativity that we think about before doing the experiment, because sometimes maybe the experiment needs a cost or ingredients that is not present. So first, try to make some hypothesis and computational data to design that material. And then the next step would be doing the lab work and measuring some other things. For example, like circular dichroism or using spectrometer or XRD to validate what we have done and what we have thought about the material design. So yes, the FT time is really small, and comparing to lab work can measure it in seconds or minutes. So it is done not parallelly, but in different functions. We can also do lab work first. So trying the Montmorillonite given in conditions, for example, given protein, solution or certain pH or certain temperature, and then we get the result from instrument measurements. And then we do the computational analysis to see what we cannot see from the experimental results, like for example, the electronic properties or the conductivity, or what happened atomically or molecularly inside the experiment that is done. So bottom line, we usually do the FT and experiment separately, like the FT to see what we cannot see from experiments, and experiments to validate so it is real in this world, not only numbers and results from computers. Maybe that's
Thank you. Thank you very much. Is there any more question? If it's not, we will try to move on to the next presenter. Thank you very much, Ilona Joan.
Thank you very much.
The next presenter I will call the Chi Kai Chen. Chi Kai Chen. Is Chi Kai Chen here? If it's not, then Rediarsa Dharma Bintara.
Okay, thank you. How are you, sir?
How are you, sir? Yeah,
Alhamdulillah,
I'm fine.
good. I'm so sorry if I come late from
How
this
are you?
meeting. Alhamdulillah.
So you will presenting the evaluating 3D printed part quality, the impact of temperature and shape object. Is it true, sir?
Yes, sure. True.
Yeah. So the presentation time is 15 minutes and the Q&A session is 5 minutes. I think you can start now. The time and place is yours. Thank you.
Okay, thank you. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Today I want to present about my research that have titled the evaluating the 3D printed part, focusing the temperature and the shape of object. I'm from the Mechanical Engineering University of Malang, Indonesia. The first one is additive manufacturing is one technology for creating the object, especially for layer by layer. It is one technology that it can be used for create object without any mold. So this is very, very easy to use to create several shape and several model. The application of this technology is create the automotive part. Some area is in civil engineering to create the building. Any application in medical also. This is to create or modify some structure of bone. The previous study, the orientation angle on layer height is one important parameter to effect on the quality of object. So in this parameter, we can modify and can observe how to impact the temperature and the shape of model to affect to influence on the quality of object after manufactured by 3D printing machine. And the first one, we can create the 3D model by CAD software. So we can modify or create something in here and save it in the STL file. After that, we can manufacture it by the 3D Ender 3 or 3D printing files to get the real part based on the 3D model that we designed before. After that, to evaluate the quality or accuracy of the 3D printed part, we can use the 3D scanning CR scan result to observe the quality and dimension, also the error of the object. After that, we can comparing the result after 3D scanning and compared with the original model. The accuracy of this result we can observe will be evaluated to get the best object. Here, I try to modify the temperature nozzle around 200 until 210 in the nozzle temperature in the Creality Enter 3 here. But the bed temperature layer height I set in the constant value like the layer height 0.25 and the bed temperature is 60. In my research, I tried to modify in different shape. The first one is cube, cylindrical, and sphere. But in here, we can control the volume between of the three model. Here I set to 8,000 millimeters cubic here. After we get the model and create the model, we can also manufacture and evaluate by 3D scanning. Here, I get some data, the distribution of error between the 3D printed part and the original model, like cube, spherical, and also cylindrical here. In here, we can get the data is the maximum of the root mean square deviation between all of the data is under 0.5 millimeter. This is I think is good enough. Even we increase the temperature, but the result is the deviation is also under 0.5 millimeter. But we can observe more detail in the bed, the flat surface on the base of spherical. This is good. Is not good enough because this is a defect. After we get manufacture 3D printed part, this is defect, and we can try to how to minimize in the next feature. The second one, we also observe in the local area, like the base of the part here. This any elephant foot model, so this is not good enough, but we can evaluate the RMSD also is under 0.5 millimeter. I try to evaluate the local area for every model, cylindrical, cube, and spherical. Is more error in occur on the spherical model. Here is not only in the base model, but the side of the model is also defect. So this is not good enough for the manufacturer and for application. Maybe in the future, I want to evaluate the spherical model and develop the some manufacturing process to repair this condition. Based on my result and my evaluated study, the nozzle temperature is that it doesn't have significant effect on the product dimension. This is indicated by the average root mean square deviation value still below 0.5 millimeter. The second one, the accuracy of the print dimension is greatly influenced by shape of the object. The printing process, the supporting structure need to be considered when make a round object, especially for spherical model. Maybe this is the conclusion for my study. Thank you for your attention. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for the presentation, Mr. Reddy. Now is the question and answer question. Is there any question from the attendees, participants? Mr. Reddy, maybe I would like to ask some question. Like, the way the temperature is not very not very impactful. What do you think the why is that happen? Like why the temperature is not really affecting affecting
On
variable.
yes, on the 3D printed model also. Yeah, maybe the first one is the temperature is on ring of the material melting. I use the PLA dan PLA polymer. The recommendation ring of the temperature is around 200 until 210. So I try to observe how to impact the temperature in 200 until the 210. Is good or not? This is my motivation first. And maybe in the future, because the temperature is not effect enough to the accuracy of the model, maybe I can try to overmelt. Overmelt is the nozzle temperature is higher to the 210 in the next future, maybe. Yeah. Because different material have the characteristic, especially for nozzle temperature. So in the PLA, I just use the 200 until 210. So maybe this is the parameter that can not affect on the accuracy. The meaning is the accuracy is also good enough. It's not higher to 0.5 millimeter. If we increase the temperature, maybe the result maybe is different. I think maybe this one my answer, Mr.
Yeah, thank you very much. Maybe
Latif.
I also have some opinion about that. Probably that the range of the temperature that measured is only 10 degrees difference. So maybe if it's have the difference is maybe 50 degrees Celsius or have a wider range, maybe it will be effect. Maybe
Okay, thank you.
I'm not really
Maybe I
sure,
can try
but
to
it's
study in the next feature.
yeah. Thank you very much for Mr. Reddy.
Thank
If there's no more question, I will move on to the next presenter. Thank you very much, Mr. Reddy. Chi Kai Chen. Chi Kai Chen is it present? Chi Kai Chen. Chi Kai Chen, Yu Wei Chen, and Hong Yu Wu. I think the presenter is not yet present. So for the next agenda is we will take a 5-minute breaks and then we will continue this event. So thank you and please stay with us. We will take a 5-minute breaks. Thank you. presenter and also one keynote speaker. The last keynote speaker. It's very we will very appreciate that if you are still with us while we try to confirm both of the speakers today. So please wait for us and hold on this event. Thank you. Maybe I will update the presenter status in 5 to 10 minutes from now. Thank you. Please stay with us. Thank you. for staying with us. I would like to say hi to Associate Professor Majid Nias Akhtar. How are you, sir?
I'm fine, Alhamdulillah. How are you, sir?
Yeah, I'm fine, thank you. It's very grateful that you can join with us. So uh, let me introduce you to the audience. Please wait a moment. So now we have our second keynote. Dr. Majid Nias Akhtar is Associate Professor in Department of Physics at the Islamia University of Bahawalpur, Pakistan. He earned his PhD in physics and also complete postdoc fellowship at uh, National University of Malaysia. And then with over 260 publications, his research has been widely recognized, accumulating more than 7,000 citations. His expertise spans from nanomaterial, ferrites, composite, X-ray diffraction, renewable energy application, with a strong focus on structural magnetic and dielectric properties of advanced material. Dr. Akhtar also has uh, collaborated extensively at national and international level, contributing to advancement in nanotechnology and material science for energy, electronic, and microwave absorption application. So thank you, Dr. Majid Nias Akhtar. Uh, you you can start the lecture for today if you are ready. Yeah, thank you.
Okay,
So,
doctor.
the
Thank you.
time, yeah, the time and place is yours. Thank you.
Okay, thank you, Dr. Ahmed, for your very excellent introduction, and thanks for providing me the opportunity to present my research work in the esteemed conference ICEFMI. So, okay. Okay. Okay, now I'm going to start and share with you my research, which I have been done in the previous 5 to 6 years. Before this, I worked on the nanomaterials for the oil and gas exploration applications, and I worked for these materials to get the target locations. So now I'm presenting my recent projects, and hopefully you will get information related to the nanomaterials and the nanotechnology, which can be used for the industrial application and the most recent communication applications as well. Okay, the talk title for today's is Versatile Nanoferites and Composites for Industrial and Technological Applications. I will start with the introduction of the magnetic materials first, and then I will introduce 3 strategies which will provide us the information related to the communication technology, absorption application, and also for the energy applications, which is a very basic need for the today's world. So first strategy will be the antenna miniaturization using the nanoferites. And the second strategy will be the nanocomposite for the microwave absorption applications. And the third strategy will be the nanocomposite ferrites for the energy applications. And then I will describe how can we basically fabricate the materials, and then by using different methods, and then how can we simulate the actual results, and simulate the our prototype and the actual results. So finally, I will share with you the results for the magnetic nanoferrites and the nanocomposites. And finally, I will conclude my talk. Okay. So as we are very much familiar that the magnetic materials are in different forms. So initially, the alnico materials, which were the neodymium magnets, and in the last 5 years, the application of these materials are we can say that these magnetic materials can be used for in the MRI, in the different applications, just like the mobile phones, in the DVDs, in the fabrications of the chips, and the wireless communication technology as well. Later on, after alnico materials, the magnetic materials, which are in the different forms, just like the soft ferrites, hard ferrites, and the semi-hard ferrites. And most of the industries are basically using these type of materials, and they are investing many of the euros, just like semi-hard materials is a very big industry and have the 15.5 billion euros. And similarly, hard materials, and the industry basically is investing the money, very big amount, 7.3 billions. And similarly, the soft materials. And these soft materials basically consists of the soft ferrites and the soft alloys and the hexaferrites. Basically, we are working on in these areas: soft ferrites, soft alloys, and the hexaferrites. So according to our first strategy, an antenna with magnetic nanoferrites. So these nanoferrites basically, which we have prepared in our lab, and these are used as a substrate material. And these materials basically will help us to reduce the size of the antenna. And these antennas can be used for the high frequency applications as well. And we can simulate these antenna by using the CST software, by using the COMSOL multiphysics software, and HFSS software, and different softwares which are based on the finite element method and FDTD, finite difference time domain methods. So these are the some figures which I have shown to you. Basically, this figure 5, you can see the geometry of the miniaturized antenna with nanoferrite material. And we have published this result in the Journal of the Physica B already. And we can see that this is the feeding point, and this is the dimension of the antenna. Basically, our nanomaterials, which is based on the different substrate materials, can just like the nickel, manganese, cobalt, and other. These are used basically substrate materials. And this material basically will help us to boost the electromagnetic properties of the antenna. And these electromagnetic properties basically can be, and the dielectric properties can be evaluated by using the vector network analyzer. And this vector network analyzer basically provide us the information in the gigahertz regime. So our first strategy will be used to use these nanomaterials in the field of the communication technology. And microstrip antenna can also be fabricated by using this technique also. Okay. Our second strategy is to use these magnetic nanocomposites for the absorption application. So we can see that basically the absorption phenomena can be seen here by, you can see that This is the basically our material, and our material can be porous material, and it can be versatile material, just like the carbon nanotubes, carbon fibers, graphene based, and magazines. Basically, in the new materials, we can combine these materials with the our soft ferrites materials or the hard ferrite materials, and then we prepare the composites. The basic phenomena of this microwave absorption is the light is incident, and it is transmitted to the material under reflected back. Basically, in the inside the material, we have electron hopping, and we have interfacial polarization, multiple reflections, and also the magnetic flux. Due to this, we basically got the losses of the material, and these losses are basically very much important to reduce the or to basically increase the reflection loss, which is the good property to get the absorption related materials. So this is a VSM, just like the VSM graph of the hard and soft components and hard and soft material with the carbon fibers as well. So this is a SCN image for to get the where the material is porous material or it is the dense material, and what is the morphology of the material. So we have published these type of materials in the well-renowned journals, which are basically Q1, Q2 journals, and we have too many papers which have been published related to the magnetic absorption. So this is the second project and the second strategy. Okay, the third strategy, which is very important for energy applications as well. So you can see the magnetic ferrites and and their composites, which can be used for the energy application. So we choose the fuel cell. Basically, how can we use these Fe based materials inside the fuel cell application? As we know that we have a anode and cathode and the electrolyte inside the fuel cell. So basically, this is the very important application, and we can we can prepare the portable basically fuel cells by using the nanomaterials, and this is a very important application of the fuel cell. We can use these fuel cells to run the cars, as many of the countries have already developed, and we can enhance the efficiency by using the fuel cell application. Later on, I will show you the results which I have obtained, and in our project we have published this in the different materials as well, in the different journals as well. Okay, so basically fuel cell have many types: proton exchange membrane fuel cells, alkaline fuel cells, phosphoric acid fuel cells, molten carbonate fuel cells, and solid oxide fuel cells. Basically, currently we are working on the SOFCs. SOFCs are the solid oxide fuel cell. This is a very important type of the fuel cell, in which we can use these type of fuel cells to get the more efficiency as compared to the other fuel cells. And one of the problem which we are currently reducing, or our main objective, is to get the low temperature solid oxide fuel cells, less than 500 degrees. So we are working on it, and basically Fe based fuel cells which can be used to enhance the efficiency of the solid oxide fuel cells as well. Okay, this is the introduction of the magnetic nanoferrites. So I have described you the three strategies in which we can use these materials for the nanotechnology applications, for the antenna communication, for the absorption application, and for the fuel cell application. So what are the magnetic nanoferrites? Magnetic nanoferrites are different types we have studied here. Basically, there are many types: spinel ferrites, garnet nanoferrites, hexagonal nanoferrites. So we are working on these types of nanoferrites Garnet, spinel and garnet, these are the category which we can use for the soft materials. Whereas in the different types of hexagonal ferrites with, which are M type, W type, X type, Z type, U type, Y type. In addition to this, we have T type also. So in among these, we have all are almost have the soft characters, but M type is the hard ferrite, which has a formula barium Fe12O19. And these SR is the basically the structure of the different blocks, spinel blocks, inverse spinel blocks. Basically, hexagonal ferrites are the composed of the different blocks of the spinel ferrites, inverse spinel ferrites, and we get the total hexagonal structure as well. So you can see the in figure A, the spinel block, and figure B, we have garnet, which have 3 lattice sites. In spinel, we have 2 lattice sites, octahedral site and the tetrahedral site, whereas for the garnet ferrites, we have that. In addition to this, we have dodecahedral site also. So in the on the right side, you can see the structure of the hexagonal ferrite, which is the you can see that the W type or M type hexagonal ferrites. Basically, this is the composition of the spinel and the inverse spinel blocks inside the hexagonal ferrites. Okay, these are the representative synthetic methods for the nanoferrites. We can prepare the nanoferrites by using the conventional method and the non-conventional methods as well. So here I described the 2 types of the non-conventional method to prepare the magnetic nanoferrites. Basically, the hydrothermal method and the sol gel method we use in our lab, and we get the variety of the magnetic nanocomposites. So this is basically, these are very general methods nowadays, and anyone can prepare. But the major advantages of using these methods over the conventional one, because they are very much simple and we can get the very good morphology, and whereas very flexible and very scalable and cost effective methods, so that we can prepare a very good type of nanomaterials as well from by using these type of materials. Okay, these are our primary results which we get for the garnet nanoferrites, and we can see that the different types of materials have been prepared. In the garnet, we can see that the formula for garnet is Y3Fe5O12. We can use the rare earth materials instead of yttrium. We can use the aluminium as well. We can use the bismuth agar, BIG, and we have already published these results in the latest our absorption applications as well, by using the garnets by substituting different dopants as well. So the morphology, we get the very good morphology for the garnet ferrite when we are increasing the temperature by from 550 degree to the 950 degree. In these images, we can see that when the temperature is less, so the agglomerations are very much higher, but as the temperature is increased, we can see the very good morphology and the very good crystalline structure as well. Okay, so these are the magnetic measurements of these. I am showing you the little bit results due to the time constraints. So just to share the idea, how can we use these materials for the different potential applications which can be used for the communication purposes and the industrial as well, industrial purposes as well. So these are the initial permeability results and the losses. So in the first strategy, we basically are emphasizing on the what is the dielectric constant. Either constant is increasing, dielectric constant on the magnetic measurements, magnetic results which are basically increasing or decreasing. But in the case of absorption, we should focus on the losses. So these are the results for the antenna miniaturizations, which we have already published in the different journals, Physica, condensed matter, already published. So these are the terbium doped nickel zinc ferrites for the MIMO antenna, multiple input, multiple output antenna. So we designed the antenna in the software, CST software, and then we get the different results. So these are the results for the experimental results, XRD, VSM, and complex permeability and the loss. But this one is the S parameter. We get the results from the designed antenna in the software. And basically the losses and the permeability and the permittivity, these are the main contributory in the reduction of the reflection loss and the S parameters for the antenna miniaturization. Okay, these are the results for the multiferrites. So when we combine the material, magnetic material with any graphene based or the carbon nanotubes, so we get the different results. So here we use the multiferrite material because multiferrites have also very good dielectric and the magnetic properties. And these are the results for the BFO and the neodymium type, neodymium doped BFO with a different concentration. We can see here, these are the TEM image of the BFO, and we can see the crystal planes as well for the high resolution TEM graph. And we can see the crystallinity. Basically, the maximum peak will result you the investigation about the structure, whether your structure is a single phase or it has the multiple peaks. So we can see that the single phase structure, but by using the neodymium and chromium inside the BFO, we can see that the number of peaks are decreasing by introducing the neodymium and the chromium. And then we also verify these results by using the software, foolproof or mod software by for the little refinement of the structure of the BSO and the ND chromium dot BFO. So we get the reflection loss, which is the minus 37.7 dB. One thing I can share with you that the major thing is to get the enhanced EAB, which is very, very important for the microwave absorption, and the low reflection loss. If the reflection loss is less than the minus 10 dB, then we can use these types of material for the better absorption in the microwave region. Okay, so these are the nanocomposite results. As I have already explained that we can use the nanoferrites and the nanocomposites. So you can see the very good morphology of the our MOS2 molybdenum sulfide. So we use previously we used the magnetic nanoferrites, and here we are using the semiconducting materials, just like oxide materials. So we can see that the reflection loss basically is very, very good, and it can be used for the X band and the KU band as well. So which is the 12 gigahertz to the 18 gigahertz. So if you use the morphological study, and if you prepare the material from the morphological point of view, then you can get the different structural properties and the different dielectric properties, and similarly you will get the outstanding results of the applications as well. So these are the reflection loss in the 3D as well for the MOS2 materials. Okay, so these are the combined calcium titanate and the nickel oxide. And similarly, for our hard material, nickel oxide and the strontium Fe12O19. So we combine these materials, and then we get we see the morphology, we get the transmittance. And similarly, the XRD results also shows the multi structure, and these are the results for the reflection loss studies. So you can see that the material can be used in the C band and the X band as well. And these are the two graphs which we can see that they're different layers. Now, these are the thickness. We are basically increasing the thickness in the software of the layer, and then we can get the different reflection loss as well. Similarly, though, by increasing the thickness, what is the effect? At the thickness of 2.5 millimeter, we can get the absorption at C band. Whereas by using the lower layer of the calcium titanate nickel oxide and the upper layer of strontium ferrite and the nickel oxide, we get the reflection loss, but it is not a good reflection loss due to the double layer. So we published these results in the Journal of Applied and Interface Science. So which is very good journal to get the information, and we have published already there. Okay, so these are the results for the gadolinium, doped copper, nickel, zinc, ferrite. So basically, we use these materials as well in the for the KU band application, and we get the morphology, very good morphology for the higher magnification or higher doping content at the 0.075. Whereas as we are basically increasing the gadolinium inside this CuNi zinc ferrite, so we can see that the magnetization decreases, but due to this, we can use these materials in the KU band application at the thickness of 2 millimeter as well. So by increasing the concentration, we are getting the lower magnetization, but in opposite to that, we are getting the higher reflection losses at the KU band. Okay, these are the results for the samarium ferrite, which we have inside this. We dope the ytterbium and lanthanum, which are the rare earths, and we basically use these materials for the fuel cell application. And we have published these results in the Journal of Hydrogen Energy and Applied Physics Letters as well. So these were the very informative and the very excellent result for the fuel cell, but when we are using the ytterbiums in the samarium ferrite. So we can see that as the temperature is increasing, we are getting the low voltage, and similarly we are getting the power density, higher power density by in the temperature range of 550 degree to the 500 degree to the 550 degree. So these are the morphology of these materials. Okay, so basically in our second strategy, in the previous case, we were using the magnetic materials for the absorption application. So here we introduced the new materials, which are the terbium doped, and we get the reflection loss by increasing the concentration in the 3 gigahertz. So we are working on the different vector network analyzers 1 to 18 gigahertz, which covers the band C band, S band, X band, KU band, and here we are working for the 1 to 6 gigahertz. So, but we are also analyzing these results by using by preparing the different absorber in the CST software as well, and we are getting the absorption in the same gigahertz range. So, which confirms that the experimental and the theoretical results, these are the very good matching for the absorption studies as well. Okay, finally, I conclude my talk because I already explained the 3 strategies. So I can say that the nanotechnology is trying to help the communication, absorption in electronics and the energy industry. So magnetic nanoferrites, by using the CNTs, these are the very good solution for the microabsorption application as well. So MIMO antenna operates in the dual frequency bands, which we have already shown you in the which work in the gigahertz range, which is from 3.5 to 5.8 and gigahertz, and it can be used for the 5th generation smartphone applications as well. Similarly, our nanocomposites, which are based on the hard and soft with the CF carbon fibers, this can be used in the minimum to get the minimum reflection loss, where we have got minus 45 dB at the frequency of 12.4 gigahertz. And the we also compare our experimental results with the theoretical results, and we can say that the reflection loss can be reduced by increasing the thickness by using the different dopants in the nanomaterials as well. Finally, SLFO, which is the electrolyte membrane, achieved higher power density and which can be compared with the other cells, fuel cells as well. I am working currently in these projects. Currently, my citations and H index is 48, citations is 8,000. And also I am working in the as a adjunct professor in the mechanical department at University Malang. So thanks for providing me the opportunity to present my talk as well. Thank you. Any questions? You are most welcome.
Yeah, thank you very much for the lecture. It's very interesting. For the attendees audience, is there any question?
I am, sir.
Oh yeah, Mr. Imam.
Okay. Thank you, Mr. Majid Nayas and Mr. Latif. I'm very interested for your presentation and your research. I have some question for you, Mr. Majid. The first is, how do nanofarad contribute to enhancing the performance of fuel cells in terms of efficiency and durability? And then could you share some insight on future research direction for nanofarad in renewable energy system? Okay, I think enough.
Okay, okay, thank you. Basically, we can enhance the fuel cell efficiency by on the working of when we are going to work on the electrolyte materials, anode materials, and the cathode material. So it is your choice whether you can use the electrolyte material. So most of the researchers are working on the electrolyte materials currently. So one of my suggestion is to use the Fe based, because most of the researchers are currently using the oxide materials. So they are doping with the different oxide materials to get the composite by using the graphene nanofibers. So I think the new direction may be that to use the magazines with the oxide materials and with the Fe based magnetic materials, so that you can get the conductivity better by using the multifluoric materials, which are Fe based, and also the homogeneity, better homogeneity in the form of the cubical shape and hexagonal shape and as well. So electrolyte material efficiency could be enhanced, or you can also change the cathode or anode material as well.
Thank you very much for the answer. So, is there any feedback, Mr. Imam? Or
Thank
is
you,
it
sir.
enough?
I think enough. Thank you. Thank you.
Yeah. Thank you very much. Is there any more question? Actually, I have one question, Mr. Majid.
Yes.
So you mentioned that dual band is 3.5 and 5.8 gigahertz. I only knew that dual band right now used is 2.5 and 5 gigahertz. Is it correct? That and then yeah. What's the yeah, I'm not the I'm not in from the electrical department, so maybe it's not a very good question. But what's the advantage moving from 2.4 gigahertz to 3.5 and move from 5 gigahertz to 5.8 gigahertz? Thank you.
Okay, thank you, Ahmad. Basically, we have the different frequency bands: S band, C band, X band, and Ku band. So every material have their properties, and we can use different materials in the different bands. So
Mm.
if you basically are, if you are working in the 1 to 6 gigahertz range, then it is in the range of C band and the S band range. And if you use your material in the 6 gigahertz to the 11 12 gigahertz, then it is in the range of X band. So for the defense purpose, you have to use the frequency range of the X band or the Ku band. And for the high frequency applications which are in the communication and for the antenna application, you can use these materials for 1 gigahertz to the 6 gigahertz. So it depends on the choice of the material, what are you doping inside this, and what are you basically planning to use these materials in the different fields. So it depends on the material properties basically, and the outcome of the material, which will describe whether we can use these materials in this range, in X band, in C band, in X band, or in the Ku band.
Yeah. Thank you very much for the answer. Is there any more question? If it's not, thank you very much for Dr. uh, Associate Professor Dr. Majid Nias Akhtar. Thank you very much for the insight and your time. Uh, you can stay in the Zoom, or if you have any more any other schedule, you can also leave the
Thank you, Ahmad, for your time and for your. Also, I'm very thankful to the conference organizer and especially Dr. Poppy Puspittasari. She helped a lot to in touch with you. So I'm very thankful to our organizers as well. Thank you very much. Thank you.
Yeah, thank you. So I think that's all for our venue. So as closing remarks, I will before the closing, I will give quick closing remarks for dear distinguished speaker, respected research, esteemed guests, and all participants. It is a great honor and pleasure to welcome all of you to Isefmi International Summit on Sustainable Energy, Functional Material, and Industry, a platform we where knowledge meets innovation and collaboration shape the future of mechanical and industrial engineering. We believe that every paper presented, every discussion, and every connection made here will be contribute to not only academic growth but also to the real world impact and in industry and society. With that spirit and with great enthusiasm, I officially declare the International Conference on Mechanical and Industrial Engineering 2025 is closed. Thank you, and may this conference be fruitful and inspiring for us all. See you again in the next ISECMI. Good afternoon, and thank you very much.